So in this video, we're going to define electric potential, and this is in chapter 26-4 of the textbook. Okay, so electric potential, or sometimes this is referred to as voltage, and we're going to use a V to stand for electric potential, and well, often we'll put a little subscript E to indicate it's an electric potential, but well, it's a scalar, and it only depends on the charge of the source. So effectively, if you remember, we had the electric force, which was Coulomb's law, K Q1 Q2 over R squared, and we divided out one of those charges to get the electric field. Well, in the last video, we defined the electric potential energy, which also had two charges in it, and effectively we're going to divide out one of those, the subject charge, and we're going to get something that only depends on the charge of the source, and that's the electric potential. So the definition of electric potential is the electric potential energy divided by charge. So units, well, energy is in joules, charge is in coulombs if we're in SI units. So the unit of electric potential is the joule per coulomb, and that's known as a volt. Okay, so some comments. Well, remember, the electric potential energy, U sub E, only changes were physically meaningful. So, similarly, since the electric potential V is defined based on the electric potential energy, only changes in the electric potential are physically meaningful also. So, and well, now if we have the electric potential, it's easy to go back to the electric potential energy because we just need to multiply by the subject charge. So the change in electric potential energy is equal to the charge, whatever charge we're moving around, times the change in electric potential. So, and just as a little side note here, so if you stare at this equation, it actually results in a very useful unit of energy, something called the electron volt. So if you take charge times electric potential, that gives you units of energy. So if we use the fundamental unit of charge E times 1 volt, so that's actually a unit of energy. So an electron volt is 1.6 times 10 to the minus 19 joules. And that's actually a handy unit of energy. It gets used in particle and atomic physics all the time. Okay, so how do we get the potential if we have the field? Well, remember in the last video, so if we want to know what's the change in electric potential energy, well, we need to do this integral from some initial position to some final position of the force dotted into our little path length element, displacement vector. So well, remember, to go from electric potential energy to electric potential, we divided out one of those charges. So if you imagine we take the electrostatic force, divide out one of those charges, well, that's just the electric field. So the electric potential, to get the change in electric potential, we need to do the integral from the initial position to the final position of the electric field dotted into our displacement vector, dr. And technically, this is what's known as a path integral. So the path integral, because you're integrating along some change in position, dr. So, however, fortunately, since the electrostatic force is conservative, remember, for conservative forces, the work done doesn't depend on the exact path. So in fact, the electric potential doesn't depend on the exact path we take here, so we can always choose that to be a straight line, or in some cases there's other convenient choices.